Even old smartphones have a high-resolution touch display combined with cameras, speakers, wireless communication, microphones and other sensors. And of course a rechargeable battery. These are components that would cost us tons of money if we wanted to buy them individually. So is there a way to save money and reuse an obsoleted phone in an electronics project? Let's see how we can do that with this 12-year-old Samsung Galaxy S2. Stay tuned. The main advantage of old devices is that they can easily be dismantled. So I first unscrew the screws. Fingernails are the best tools for separating the shells, as they do not leave any dents or marks in the material. Now we could try soldering wires to the side push buttons to use them as inputs. The buttons are made of a spring metal foil that closes the contact when pressed. But attaching some wires would most likely destroy them, so I quickly abandoned this idea. And using the flashlight LED as an output did also turn out as not feasible. I did not see a single way to solder wires to its contacts, so I had to find another solution. Finally I came up with these USB serial adapter boards. Their FT232R chip has RX and TX for the UART protocol, but also 6 modem control pins. This gives us a total of 8 pins that can either be used as digital inputs or outputs. With an OTG adapter cable we can easily connect it to a mobile device running Android 3.0 or a later version. Now I go ahead and stick 4 LEDs and their series resistor into a breadboard. And I connect the anode of each LED to the 8 I/O pins of the module. These can either take the role of an output or of an input. It depends on how they are wired. When configured as an output, the pin provides an open collector stage. If the transistor is blocked, current can flow through the LED and the resistor. Otherwise, the transistor shorts the LED and the LED goes off. To get an input, the pin must be pulled to ground with a resistor between 10 and 47 kΩ. So I wire the remaining pins as inputs. Speaking about electronics, here I want to thank the sponsor of this video, PCBWay. Simply upload your Gerber files directly from KiCad to their homepage, specify your requirements, and a few days later the boards will arrive. I love their high quality PCBs, and that's why I love to work with PCBWay. Soldering is always fun and done in no time, even for beginners. And PCBWay not only makes PCBs, they do also offer CNC machining, sheet metal works, 3D printing and injection molding. Get everything you need for your awesome projects from one hand. So give them a try. And now let's write a little Android app that lets these LEDs blink. Shall we?
Do it! Just do it!
This can be done with the free Android Studio, which can be downloaded from the Android developer site. After you have started the program for the first time, choose Get from VCS and enter this URL and make sure that Git is set as a version control system. Then clone the repository to your PC. Now the Gradle build system starts to create the project files. Click here to add some of the generated files to your local repository. It takes a little while until the project files have been created, but then we are ready to go. It has resource files. Sketch.point Java reminds of an Arduino sketch, doesn't it? Here we can use some of the commands that we know from the Arduino framework, like digital read, digital write, and so on. This is where the actual logic takes place. USB I/O service.point Java provides a background service that does the actual communication to the FTDI board. It implements the Arduino functions and executes them. There, a thread repeatedly calls a loop function in the Arduino sketch. A second thread keeps a variable in sync with the actual levels on the FTDI pins, so they can always be written and read by the appropriate Arduino functions. The user interface of the app is coded in the main activity. When the app has just been opened, Android calls its onCreate function. There it draws all the UI elements. Their positions and properties are defined in an XML file. Luckily, you don't need to tackle with this file. Android Studio also includes a graphical editor that allows to build an UI in a convenient way. Here we can position the widgets by aligning them with the frame and neighboring elements. So we make sure that the layout looks decent with all screen resolutions and aspect ratios. And we can of course customize them to our taste. That was easy. What we want to do now is to download and run the app on a phone. First, I connect USB. Then I touch the gear symbol to open the settings. There I scroll down the list until the developer options. I enable these and confirm my decision, then I check the check mark next to USB debugging. One more OK, and that's it. A few seconds later the device name appears at the top of the Android Studio. Clicking on the little green triangle does start the upload. There is the app. We need to connect our LED circuit now. Then give it the permission to access the USB device. Now I can switch on and off these LEDs with the buttons. But hold on, there is still an issue that we haven't considered yet. The USB port of the phone supplies the attached electronics with power. That means that the battery will be drained faster than we would normally expect. If we connect the power supply to the plus and minus rails, it only supplies the circuit but not the phone itself. So if we want a permanent power supply and have no separate charging contacts or contactless charging, we need to expose the battery contacts and apply external power there. It's an advantage if the phone has a replaceable battery. This one is easy to open and the battery comes out almost by itself. The imprint shows the pins to connect and their polarity. Now we know where to connect an external power source. I could have just soldered wires to the contacts, but I didn't want to risk ruining them. Instead I cut a piece of strip board to fit into the cavity for the battery. The blobs of soldering tin provide reliable contact there. So we can power the phone through these two wires here. The voltage of a lithium-ion battery is usually between 2.5 and 4.1 volts. So it will be fine if we power it with 4 volts. I think the voltage regulator can also handle 5 volts, but I don't want to risk blowing it up.
God, please, no!
To be on the safe side, I take a DC-DC converter and adjust it to 4 volts. Now I dare to connect the phone and turn it on. Here I have opened the app again, so checking the checkboxes lets the LEDs blink. And with all checkboxes set, we get a running light. The slider changes its speed. See how fast it can go. Now look at the radio buttons below. When I connect the input pins to the positive rail, their bullets appear. Here's again the Arduino-like code that lets these LEDs blink. You can use this as a template for your own apps. I'd love to hear your ideas. What projects could you use this for? Please leave your comments below. And as you've made it this far in this video, please hit the like button to recommend it to others. Also subscribe and enable notifications so you never miss out on my latest projects. You can even support the channel on Patreon and get ad-free previews. Thank you for watching.